This is also the first one for me in this format, so it's as interesting for me as it is for you. This will be a talk on the safety of neural networks. So to talk about safety of neural networks, I'll first kind of introduce the concept of safety. What is safety? Then the concept of neural networks. What is neural networks? And then we'll be able to talk about the safety of neural networks. So what is safety? This is what Oxford Dictionary says: the condition of being protected from or unlikely to cause danger, risk, or injury. So we don't care about neural networks being protected from something. We care about them to not cause any danger, risk, or injury. And the important word here is unlikely. So it doesn't say that safety is that it will not cause danger, risk, or injury, because we cannot actually guarantee it. So safety is talking about something in the future. Welcome, Alexei. And a future is always uncertain. We cannot predict anything in the future with 100% certainty. So when we talk about safety, we talk about probability of failure. We cannot prove that anything is perfectly safe. And sometimes people use this as a question, like, how can you prove that something is safe? In real world, we cannot prove anything. Proofs exist in the domain of mathematics. In mathematics, we can prove that the unit circle has a length of 2 pi, but we cannot prove that the sun will rise tomorrow. We can only estimate that probably it will, but we cannot prove it. So safety, when we build a safety argument, when we try to demonstrate that something is safe, it is a story. So safety argument is a story. This is actually what FAA, Federal Aviation Administration people told me on one of our meetings when we were talking about certifying aviation equipment. That safety is a story we tell about how we made sure that we understood what is the probability of failure of subsystem, when it can fail, in what conditions, how we tested that, and so on. So let's talk a little bit about safety in aerospace, because I work in aerospace, and also because it's a striking example. So this is a fantastic machine. Recently, I had one person told me that we have shuttles, like, why don't we still fly in space, don't fly in space, or don't have air taxis or whatever. So actually, this fantastic machine killed more than 1% of people who flew it. So while this level of safety may be acceptable for space exploration, probably you will not use it as your transport to work, or something you go on vacation. So this machine is not so glamorous, but it is more than 100,000 times more safe. So while they look similar, and shuttle is maybe looks cooler, it can go to space, unlike Airbus A320, they are not even in the same ballpark of what engineering required to build each machine. To reach 100 times safety, more safety in one machine than another, you need to use radically different processes and approaches to everything. You cannot use the same pilots, you cannot use the same maintenance, you cannot use the same operations, you cannot use the same engines, because any of those things on the shuttle are unsafe in the context of having a public transportation system. Public transportation requires radically different levels of safety. And so safety is always for a particular application, let's say it this way. In aviation, we have a concept of design assurance levels, DALs. And the highest is DAL A. We go from DAL E, which means that it doesn't matter for safety. It's maybe your entertainment system or your headphones in your economic class, to DAL-A. DAL-A is the systems that can cause the aircraft to crash and kill everybody on board. And when we make a story of safety to the design assurance level A, we have to demonstrate that the probability of failure is 1 per billion hours of flights. And this is completely ridiculous number. Like, it's impossible to test for 1 billion hours. This A320, in its 35-year service record, it first flew in 1987. And it's one of the most popular airliners in the world. And still it only flew less than 1 billion hours total. And still it fails more than once in 1 billion hours, right? So it had 14 crashes, not one. So, of course, even when we certify something to DAL-A and demonstrate that in our story, the probability of failure is 1 in 1 billion hours, of course, in reality, it will not be so. People are not perfect. We make some mistakes in our story. People will make mistakes in operation. So the actual probability of failure will be higher, but still, pretty good. So when we make a story about it failing at this rate, that story is not perfect, but it's much better than having no story. So how do we estimate safety of something? So here we have a very nice video. Maybe you have seen these things in IKEA. So this device, actually, very similar devices are used to test safety of things. It opens and closes the door and does it a lot of times, thousands of times. And so when it does it, we can record how many times was it successful, when it starts to fail. The important thing here is that there is some weight there, you see? 5 kilos, in Vava it's 3 kilos. So it's important that when we make this testing, it must be in realistic scenario. That we, for example, if these devices will be operated at room temperature, it makes sense to test them at room temperature. But if they will be operated at altitude of 10 kilometers with temperature of -50, then we should test them in those conditions. So when we test, we need to test a lot, and we need to test in relevant conditions. And that allows us to estimate how often will it fail, when exactly will it fail, in which conditions. So another thing is when we do this, right, it's completely impossible to test that for 1 billion hours. So how do we arrive from this kind of testing that tells us, okay, we did this 10,000 times and 5 times out of that it failed. So we have 5 out of 10,000. How do we arrive from this number to estimate that something will fail no more than once in 1 billion hours of operation? So here we get to the system testing. So this is an example of a system for an Apollo control unit. So Apollo aircraft, of course, this is incomplete, but the important thing is that there is a lot of components that are connected with each other. And each of these components individually can be tested using that earlier method. We can say that we tested, say, scanning telescope and found that it fails this many times, right? And we tested Apollo guidance computers and it fails this many times out of, I don't know, 1 million hours of operation. And so when we propagate these failures through the system, so we see, okay, this component fails this many times, and then its failures will propagate for Apollo guidance computer, and maybe Apollo guidance computer can actually compensate and see that if it fails, other things still do not fail, and so probability of failure will be lower on the output, and so on and so on. And so out of the failures that we learned with testing of individual components, we can arrive at the probability of failure for the whole system. And we can, by adjusting how we arrange these components, we can actually make that probability much lower. So, for example, I'll go back. So there are some differences between these two aircraft that maybe can help us. For example, they both seem to have a few engines, right? The Airbus has 2 engines, and the shuttle has 2 engines. But the Airbus has engines on the pylons under wings. And actually, all the airliners have engines on the pylons under wings, actually in front of the wings, not under the wings, but in front of them. So why is that? The reason is that if one of these engines blows up, if one of the engines on the shuttle blows up, it will blow up all the other engines because they're located in the same place. So failure of any one of the engine will cause the loss of the aircraft. On the Airbus, if one of the engines blows up, first of all, it will not affect the other engine. Second, because it's on a pylon that is in front of a wing, it will probably not even affect the wing itself. And the aircraft is designed in such a way that it can land with only one engine at any time on its route. And besides that, what we don't see here is that the section of the fuselage that is at the same kind of plane as the engine, it's actually reinforced. So if some turbine blade from the engine will fly out, if the engine blows up, its turbine blades can fly out. They will hit reinforced section of the fuselage and are unlikely to cause failure of the whole aircraft. So even if the engine does not have this probability of failure 1 per billion, it has much higher probability of failure. But the overall aircraft can achieve it. So this is also called common mode failure. It's when failure of one component can cause failure of another, or when components are similar, and in this way they can fail at the same time for another reason. For example, here we have a national measurement unit, right? And maybe we could have 3 of them to verify that, if one fails, then the others can save us. But if this national measurement unit, some common mode failure, for example, they all stop working in pre-fall conditions, or when temperature gets higher than 50 degrees, right? Then it kind of destroys their independence. We can no longer multiply their probabilities of failure because they can fail at the same moment. Another very important thing here is that it's very important to know when something fails. So for example, with the example of this national measurement unit, imagine that we have 2 of them. There is a big difference between having one of them fail and we just, we see that it fails and we switch to another one. Or it's just giving us wrong measurements, but we don't know that it failed, right? In the second case, we will make wrong decisions, we'll make wrong inputs to our control system, and so the rocket will not fly up and can crash, or the shuttle, or the plane. And if we detect the failure, we can much easier compensate for it. So generally, it's much, much safer to have a system that can detect its own failures. For that reason, on aircraft, in the cabin, you see a lot of kind of lights that every single component on that aircraft has some check that tells when it fails. So the pilots know and can compensate for it. And of course, we still need to do the testing of the whole system. So the Airbus needed to fly, to do test flights, but those test flights are nowhere near enough to kind of build the overall safety argument. You cannot fly for 1 billion hours. It didn't fly 1 billion hours in 35 years with all the thousands of units that were produced. So it's only a little bit of end-to-end testing. Most of the safety argument is built using testing individual components and then propagating the errors and failures through the whole system and analyzing the system in this way. So another important thing to note here is that In this way, we can actually build a very reliable system out of unreliable components. These natural measurement units, they can now be bought very cheap. For example, we use these small Bosch devices that are $6 each. They're dirt cheap. They're also not very good. But since they're cheap, we can actually put a lot of them. We can put 10 of them. And suddenly, just because we put 10 of them, we have a much, much more robust system. It will have much higher precision. It will have much better safety when we integrate all of their measurements together. If we go back a little bit again, so this aircraft A320, it has 5 control computers. So compared to the cost of aircraft, control computers are cheap. So it has 5 of them doing absolutely the same thing, running in parallel. They are of 2 different kinds, built by 2 different teams, just so that they don't have a common mode failure. So if one team made some bugs, made some mistake, and one type of a computer will fail in a particular situation, it will not probably fail in exactly the same moment in the computer that is built by another team. And this is how this aircraft can achieve this absolutely ridiculous safety level. Absolutely ridiculous if you think of it, that we are sitting on a fast-moving aluminum tube on a 50 tons of jet fuel at the altitude of 10,000 meters for many hours, and still it reaches its destination a lot, right? And practically never fails. So the takeaway about safety is that, first of all, there are no proofs. It's a story. Story we tell about the likelihood of failure. We need to test components many times, and we need to cover with these tests the operating domain. This is very important. So we need to actually test in all the conditions we expect the system to operate. We need to propagate errors, and we need to detect errors if possible. Any questions so far? Okay. Yes.
Sorry, Grigory, was looking too long for the bottom. Actually, my question is the events of failures in real environment are quite rare and probably quite expensive. Do you use, the idea is to use something synthetic or Bayesian or somehow to replace the real testament, what you mentioned with real airplane? It's nearly impossible, right, to do this.
So we test, so each of different components require different kinds of tests, right? So if we test, for example, the scanning telescope, right, we probably want to test how it actually, what it actually sees. So we need to build some chamber with stars, or maybe point it to the sky at night. If we test the guidance computer as a component, of course, then we can simulate the inputs to it, or record the inputs in real environments and then replay them to test it. So the way to test a specific component is dependent on what component it is.
So you assume independence between failure of the components, right? Like at least as a
you need. So we do not assume independence, but we need to understand the dependence. So we need to carefully analyze the system and think, in what situations can we have a common mode failure? We try to eliminate it, of course, as much as possible. And when we have probabilities of failure for individual components, and then if we know this, when the common mode failure can occur, and what are the probabilities of failure of individual components, we can compute the probabilities of failure for the whole system. Yes.
Yeah, I have a question. You said there are 14 crashes for Airbus A320, right? Out of 119 million
Yes.
flights or something.
Yes.
Are these crashes are only about like technical crashes, like not because of pilot issues, because there are also some crashes with A320. The pilot crashed the plane actually deliberately. So do you count these crashes as well, or is it only technical?
I think this number actually accounts for everything, but when we think about aircraft, we think about it as a complete system, including pilots. So
Oh, I
pilots
see. Yeah.
are part of the system. And
I
so their
see.
training, their experience, what are they allowed to do, that there are two of them, actually.
I see.
One pilot can totally fly this aircraft, right? But we
Yeah.
require to have two of them in
Yeah.
the cabin. This is also a safety.
Yeah, it's like having two engines. Like if one fails, the other one can still fly the plane. And if
Exactly.
we have two pilots, if someone goes incapacitated, then the other can fly the plane. So
Exactly.
yeah, okay, you count them as well. So okay, that was my question. Okay, thank you.
Mhm. Yes.
Sorry for disturbing. May I ask? You only consider like, so do you consider time dimensions? So can be like multiple failures, like of the
Yes.
same.
Yes. So when we consider common mode failure, there is a version of that called self-correlation, right? So if we have, for example, component, this is also very useful for IMUs, for example. So some components give their output a lot during the second. You can take 2,000 measurements from IMU in a single second. And this is kind of in some way similar to having 2,000 IMUs that give you one measurement every second. So if we actually need to give output only once per second, we can kind of average them. But of course, we also need to consider that if it fails, probably it will give all the second will be wrong, right? It will not fail on only one measurement in a second. So all of these effects in time dimension 2 has to be very carefully analyzed to understand the overall probability of failure for a system.
Yes, personally, I think about cascading effects. Whether they arise here, I don't know, but in principle, they can, right?
Yeah, it's also analyzed, and this is what I tried to cover in common mode failure, right? So this is why the engines are separated on the aircraft, but not separated on the shuttle, because on shuttle they didn't care that much about safety. So they can easily have a cascading failure when one engine fails and it blows up all the other engines because they're located in the same place. So all of this has to be analyzed. That's true. So let's move to neural networks. What are neural networks? So neural networks are, when we talk about them, we usually mean artificial neural networks. Artificial neural networks consist of artificial neurons which are inspired by real neurons. So in our head, we have these cells that are called neurons, and these can be very long. They have these dendrites, which are kind of inputs. It connects these dendrites with other neurons and kind of senses through them what the other neuron does or outputs. And then it has one axon, so one output. And then it has these axon terminals. So this output can be then used by many different neurons. So the key is that it takes a lot of inputs. In one biological neuron can actually have like 70,000 inputs. And it produces some output that can be used by the other neuron. So we model this in with our artificial neuron in a very, very simplistic way. Of course, this is much simpler than a real neuron, but surprisingly, it already is very good for solving a lot of tasks. So we have this artificial neuron, and we want to compute its output based on its inputs. What we do is just we multiply each input to by some coefficient, then sum them up. So we make a weighted sum of its inputs. And then we apply some function to it. Function can be very simple. For example, this is a real loop. So we just take this sum as it is, if it's bigger than 0, or we say that if the sum arrived at smaller than 0, we just output 0. And that's it, that's our output. So I wrote a formula here. So this is the formula that describes the output of one artificial neuron. We just take first input multiplied by first coefficient, second input multiplied by second, third input by second, by third. Then we add some bias term, which I call here by k0, just some other coefficient. And then we output that if it's bigger than 0. Surprisingly, if we start connecting these neurons in large numbers, we get some very, very interesting properties out of these neural networks. So there is no particular reason to connect them in layers, but when we think about these neural networks, it's much easier to reason about them if we connect them in layers. So usually artificial neural networks are separated in layers. In this case, we have each layer, each neuron in a particular layer, using inputs from all the neurons of a previous layer. So it takes output of every neuron of a previous layer, sums them up with some coefficients, and outputs that as its output. The key here is that we need to come up with some good coefficients, right? So there can be many neural networks with the same number of neurons corrected in the same way, but doing very different things. One can be detecting people, another detecting, I don't know, cats, the third one detecting cars or street signs. So these networks, they can have the same architecture, but they differ in these coefficients. So how do we come up with good coefficients? So let's do a small exercise and train a neural network consisting of one neuron. So I want to train a neural network that basically puts gas on or off based on the signal of traffic light. We encode the traffic light as our three inputs. So if the red is on, it's 1. If it's off, it's 0. The second is for yellow. The third one is for green, right? Then we sum them up with some coefficients, which we initially put at 0. In practice, we usually initialize with some random numbers. And then we arrive to the output. And the output should be 0 if we should stop, and 1 if we should go. So we start training this neural network, and we see that we give it example of a green light. So our inputs are 0, 0, 1, and it outputs 0. But we actually know that we have 1. So we have this training example that we have prepared for this neural network that says, okay, when we have this set of lights, the output should be 1. During training, we see that it's currently 0. So we think, okay, how do we modify the coefficients so the output becomes bigger, kind of closer to 1? We see that the first coefficient actually will not help because its input is 0, so it doesn't matter what we will put here. The second also. But the third one, if we increase it, the output will rise, right? And the K0 is also will rise if we increase. So let's increase them a little bit. Not by a lot, but a little bit, right? So we increase them by, say, 0.3, and so the output now is 0.6. Now we show this neural network a second training example. So this time the output arrives at 0.0, but we know that it should be 0. So let's look, how can we modify the coefficients so it's kind of closer to 0, right? So we actually can get closer to 0 if we make K1 smaller and also K0 smaller. So we make them a little bit smaller. And it is not that much rock now, right? It's just 0.3, so we modify them a little bit. Now we have a yellow light, and we say that, okay, now on yellow we can still drive. For example, this is our decision when we train the neural network, how to label this data, what we actually teach to the neural network. Do we want it to drive on yellow? Do we want it to stop on yellow? In this case, I decided that I wanted to drive on yellow. So we repeat the process, and we actually have to adjust these two coefficients up. Right? So by now we have some, basically we trained it a little bit, right? So we have, and we can already see that it kind of makes sense. So the first coefficient that is associated with a red light, it's negative. It means that when we have red light on, we'll probably not drive as fast, right? It will grow more and more negative. Basically, it will notice that all the time we see red, example, we should not drive, so coefficient will become smaller and smaller. And when we see yellow, green, we should drive. So these coefficients will actually go higher. And when we test this neural network on example that we haven't seen in training, so remember, we trained only on single lights, right? We trained on red, yellow, or green. And now we show input that was not considered in training. We didn't have this sample. But it actually provides a reasonable answer. It says, yeah, you can kind of drive, I think. So this is the main quality of a neural network, that it can generalize, that we didn't have to show it exactly everything that it could experience in real life, that it can understand some patterns that happen in real life and can generalize to the stuff that it hasn't seen yet. And what about the other layers, right? So in this way, we can train the last neuron that produces the output. So we can do the same trick for inputs. We can see, okay, we have got 0.8 here, but what we wanted is 1, right? So we want the number to be higher. So how do we actually need to modify this time, not coefficients, but inputs, right? The first input should be smaller to get a high number on the output. The second input should be higher. Third input should also be higher. And these inputs are outputs of the previous layer. So we can now repeat this process for the previous layer, and then for the previous layer, and so on until the first layer. This training algorithm is called backpropagation algorithm. In mathematical terms, it means that we compute partial derivatives with respect to the output of a neural network, with respect to all coefficients of a neural network. And we modify the coefficients in such a way that the output is closer to what we want it to be. In biological neural networks, there is, by the way, no such mechanism. Biological neural networks trained with a completely different way. But okay, we use what works. So now you know what are neural networks. If you ever wondered, you now know how they work. This is it. This is all we do, right? We compute with some multiplications, comparisons. That's it. So what is the takeaway for this talk is that, first of all, yes, it's just math. It's just some multiplication, some simple mathematical operations, and there is nothing else in this neural network. It requires a lot of labeled data to train. So when I was explaining how do we train this neural network, we needed the input example, right? And we needed the right answer. There is a way to train neural networks when there is no right answer. For example, we can pit them against each other and just see which one wins. This is how AlphaGo, for example, trains. Or there are other tricks that we can use. But most of the time, for practical situations, we actually need a lot of labeled data. So in our company, we have maybe 10 people whose job is just to mark on images, circle or square around the plane or where the runway is. They provide these labels for the neural networks to train. And we need a ton of them. So you saw that we need several samples to train one neuron. And if we have neural network with millions of neurons, then we need millions of samples to train it to do something useful. It's capable of generalization. So it didn't need to see every single possible input, right? We don't program individual neurons. So afterwards, after we train the neural network, we can kind of probe what this neuron actually, what does it react to? What kind of image makes it respond very high? And we can understand what it does. But when we train, it's random. Which neuron gets what? We don't individually control them. So this last thing is my personal kind of way of thinking about neural network that helps me. It's that each next layer adds a level of abstraction. So imagine that you have an image as your input, right? So the first layer can only compare and look at individual pixel values. But it can see, okay, I have a dark pixel on the left, then bright pixel, then I have dark pixel on the right. So that looks like, some kind of vertical line, right? Dark on the left, bright on the right, bright in the middle, dark on the right. So I can have a neuron that detects vertical lines or horizontal lines, some very simple thing. And next layer, it receives the output of the first layer, right? So it says, okay, I have a horizontal line here and a vertical line here. So it looks like I have something like an angle, something like a corner, right? And the next layer can say, okay, I have a corner here, corner here, corner here, corner here. It looks like a square. And the next layer can say, okay, I have a square here and a triangle here and so on. And so at some point, we will have a layer that says, okay, there's an eye here, a nose here, and a mouth here. And the next layer can see, okay, if we have that combination, then probably we have a face. And the next layer can say, okay, we have a face here and a face there. This looks like a conversation. So each next layer adds a level of abstraction to understanding of the input. The more layers you have, the higher level of abstraction you can achieve that the network can output. Any questions about neural networks? Okay, good. So let's apply the concept of safety that we talked about in the beginning to the concept of neural networks. So the first thing to understand is that neural network is always one component of a larger system, right? So in that Apollo scheme of things, it can be one box there. So for example, we have a system that detects our aircraft. And for real, we have this system at Daedalean. And it consists of a camera, or actually multiple cameras that look outside. They collect images, 12 megapixel images, that are input to the neural network. The neural network looks for planes in this image. Then we have a piece called tracker. This piece actually does the time dimension integration that we talked about before. So it sees that, okay, on this frame, we got detections here, and on the next frame, the neural network made the detections there, and they try to form some kind of tracks that, okay, we actually have an aircraft that flies here, and another aircraft that flies there. And the output looks like this. So this is actual result of how the system works. So you see there is a number, right? So next to the box, we have some percentage. So this is percentage. It reflects the uncertainty, how certain the neural network is after propagating all its errors through the tracker, through everything, that there is actually a plane. So, right, so to kind of be able to compute overall system performance and probability of failure, we need to understand very well this box, this neural network. We don't need to be 100% correct all the time. That's not the point. As we explained earlier, absolute safety doesn't exist. But it's very important to understand what are its errors, understand how and when it can fail exactly, what is the probability of failure in all possible conditions that we can experience. And very importantly, we need to preferably detect when it fails. So if it, if it arrives in a situation where it sees something that it should not be seen, I don't know, if it sees a Mickey Mouse cartoon, it should not just try to detect planes in that cartoon. It should say, I have no idea what am I seeing here. It's not what I'm supposed to see. I'm just failed. So first, how do we do it? First, let's talk about error estimation. So the easiest thing to do, and the first thing to do, is to test on a ton of data. So remember that thing that was moving boxes on IKEA furniture. So we do exactly the same thing. We show it a lot and a lot of images and test how well it performs. And since we needed a lot and a lot of these labeled images to train anyway, this is kind of, we have it anyway, right? So we should not be using, for test, we should not be using the same images that we trained on. We should be using different images. So the way we do it, we collected a huge number of these labeled images. When we say, okay, on this, I don't know, 80% we train, 70%. And we set aside these 20 or 30% of data that we will not be using in training. And we will only use it to test in the end and understand how it performs on images that it has never seen. And how it performs on images that it has never seen can tell us something about how it will perform in the wild. And of course, it's very important that these images come from operating domain, that we didn't just, draw these planes by hand on a piece of paper, that they actually look like the planes that it will see in the wild. So we use for this testing, we use the data that is actually captured in flight using the very same camera that is will be used on the system. And we need to verify that it covers the relevant domain. So here on the right is, for example, the example of a coverage plot. It's for a different system, for a landing system. But it shows what was the azimuth, where the plane looked like relative to the runway, and what was the roll, how it rolled at the time, right? So it shows that most of the samples were actually, we were looking along the runway and were level, but which is correct, which is good, because this reflects the usual situation of a landing plane. It usually looks along the runway and has zero roll. But we have samples that cover this, area pretty well. So the network during the testing, we have tested that it works also when the roll is high, when the azimuth is off, when the aircraft was in a weird position. And we do this for a lot of different parameters. We verify that it works in the dark, that it works in bad weather, that it works on different runway, that it works with the mountains, see in the background, it works on well-marked runways, non-well-marked runways, and so on. So we test, we need to make sure that our test samples cover what it can see in the wild reasonably well. So based on this testing, we can estimate when and how it fails, in the sense that what is the probability that it gives a wrong answer, and what is the the average errors. So of course, these are numbers. So when it says that there is a plane, it gives not the exact coordinates, maybe of a plane, not exact size or not exact distance to it, right? And based on this testing, we can understand what kind of errors can we expect from the neural network. And also there is a trick that we can actually make the network just output its own errors. So I will not go into details how it's done, but we can make it, the network itself, with every detection it outputs, it can say, yeah, this plane is here, plus minus 5 pixels. And its size is this, plus minus 3 pixels, and the distance is this, plus minus 200 meters. And then we can calibrate with its own estimate, and then we can use this estimate in the rest of the system when we propagate this through the filter, through the control to the final output of the system. So this is one way to understand its errors. Another way is that we need to enforce smoothness. So the crucial thing is we need to understand when and how it fails, right? And imagine that we have these samples, right? So here, just for this graph, let's have one input, one output for simplicity. So we have these dots, they represent samples, right? So good neural network, it will approximate them using some kind of this smooth curve. But it can happen that the neural network will actually make this kind of curve, right? So it will give very good answer on all the samples we trained on. But if we select some sample that we didn't train on, that is very, very similar to some samples that we trained on, it suddenly gives hugely wrong answer. This is a very practical situation, and adversarial attacks exploit this situation. So maybe you have seen these funny videos when people carry some kind of picture on them, and suddenly networks stop recognizing them as people and recognizes them as giraffe or something. So here we have an example that we have a panda image, and we make tiny adjustment to the colors. So this is the mask, but it represents just tiny change that is barely perceptible. So we arrive at this image. And suddenly, for this image, the same neural network tells that it's not a panda, it's a gibbon. So they have found this kind of peak. And of course, to do this kind of exploit attack, you need to know exactly the neural network you're attacking. It's impossible to do for any neural network to know what you're attacking. But it's also easy to protect from this. So what we need to do is we need to enforce some kind of smoothness of a neural network output. It actually doesn't have this peak that looks more like that. So the easiest way to do this smoothness is we can, for example, just penalize neural network for having big coefficients. So remember when we trained that neural network, right? So in order to have this huge peak, you need some big coefficient somewhere, but you change the input a little bit and the output changes a lot. There is some very large coefficient somewhere. And so if we just make neural network train in such a way that all the coefficients are small, then it will be smooth. And this kind of techniques that enforce smoothness of an output of a neural network called regularization. There are many different ways to do this, but they all kind of try to make the output smooth. And once it is smooth, once we can estimate its smoothness. So remember that we have no proofs in the real world, but neural network itself is a mathematical construct. It's just additions, multiplications, and comparisons. So it's a mathematical construct. So for neural network itself, we actually can have some mathematical guarantees. For example, we can estimate and prove its smoothness. We can say that, okay, we have trained it in such a way that we guarantee that for a small change in the input, it will not have bigger than this change in the output. And then so we kind of can make a small circle around each point where we guarantee that the output will be good, will be correct. Not just at the point itself, but a little bit around it. And now if we have a lot of these points, and each has a little circle where we can guarantee the output, we kind of can fill the space. It doesn't really fill the space, but it allows us to have some very good guarantees about the output. So this is mathematical generalization guarantees that we can apply on top of the testing we have done. So another thing we can do, so all I'm talking about is building this story, right? We're building a story about the safety of a neural network. What can we do to understand its failures, understand its errors, and make sure that there are not too many of them. So another thing we can do is use augmentations. So for example, here on the left, I have a real image that we captured in flight. And here on the right, I have some versions of this image that we generated from this image on the left. We made it a little bit darker and a little bit lighter. We blurred it a little bit. We squeezed it in different ways. We rotated it. So we can modify this image. And so from one image that we actually captured in flight, and capturing images in flight is actually expensive. You need to fly a real plane with a real equipment a lot. It's expensive. So we can actually blow it up and generate a lot of training samples, different training samples. So this is called augmentations. And we actually, every time we show this image to a neural network during training, which can be thousands of times for one image, we show a different version of it that is modified in some ways that it should learn to ignore. So the point of doing these augmentations is it should learn to ignore stuff that is irrelevant. It should learn to ignore that whatever, how is it a little bit dark, a little bit lighter, a little bit this kind of noise, blurry or not, it should still do the same job. So in this way, using augmentations, we'll teach it to ignore irrelevant stuff, and we can then verify that it actually ignores irrelevant stuff. And one way to do it is doing salience analysis. So we can show an image of a runway to a neural network, and then we can see how much the output changes if we change the input a little bit. So we can see, what if we change pixels here? Does the output change? No. What if we change here? Does the output change? No. What if we change here? Oh, output actually changes a lot. So we can, in this way, we can actually see what parts of the image matter for the output. What parts of the image does the network look at to decide its output? And here we see that when it tries to find out a runway, for example, it actually looks at the corners, which is exactly what we need. We needed to look at the corners. Every runway has corners. That's how people do it. That's exactly what we would expect from a neural network that is trained to detect runways. So the next kind of technique is out of distribution detection. So remember that we want our component to be able to detect when it fails, right? When it sees something for which it cannot give a good prediction. For example, there is no runway in the image, right? And we're asking, and one of its outputs is, I don't know, distance to the runway, right? And there is no runway. So it cannot give a good answer. We need to know that it actually cannot give a good answer. Or we show Mickey Mouse image to a neural network that is trained to detect planes, right? There is no good answer for where is the planes in this image. There can be no planes. So this is called out of distribution detection. So when we trained on some images that belong to some domain. So in our case, it's images captured with 12 megapixel camera in flight on Earth. This is the domain, right? These images are represented by these dots. And what happens when we show an image that is very far away from this domain? Actually, the neural network, it can give any answer. So this here, all the lines will represent some neural networks that can be trained on this data, right? They will all have this very similar answer within the domain, but they can give wildly different answers outside of domain. And this we can actually use to detect when the situation occurs. So we can train not one neural network, but we can train multiple of them, several of them, in exactly the same way. We will show the same data set to networks. They will only differ maybe in what was the initial coefficients, which are random, or maybe in what order we showed them these examples, or what augmentations exactly were used on each sample, and so on. So we trained several versions of these neural networks. So within the domain, we test them, and they all work very well, right? So they will all agree there. But outside of the domain, there is no reason for them to agree. So this means that in flight, we can run all of these neural networks. And in fact, we don't even need to train the full neural network. We can train only part of it, some layers of it differently to achieve this effect. We can see that they start to disagree a lot. And when they start to disagree a lot, we understand that these neural networks actually cannot give a good answer for this image. And we just say that, okay, our neural network component has failed. It cannot work right now. So that's it. Any questions? Yes.
Yeah, Grigory, I have several of them. Probably ask one or two to let others ask. So one question to the previous slide with ensemble of neural networks. Actually, it just resembles very much what like Bayesian people do when they're trying to do Bayesian neural networks and have priors and posteriors and try to track them. So probably what you do is like a dirty variant of this, right?
Yes.
Yeah, yeah. If I'm allowed, I'll ask one more. Ksenia, you are supreme command.
Go ahead.
Okay. One more question is regarding architecture of your neural network. If you go to the slide when you have this tracker on top of the neural network, that means that you do not let so you basically train on images, not on videos. So you don't like to let neural network to capture the time correlations or time features like between two different frames, and you have a separate component of tracker. Why do you do this?
So one reason is that it's hard enough to reason about filling the domain with images. It's much harder to fill the domain with sequences of images, right? So these images are already huge. They're 12 megapixels, 12 million pixels each is RGB, so it's 48 million input values to a neural network. And if we now make it work on videos, when we multiply it by a number of frames, right? So now we need to fill the space, the operating space, right, with all possible sequences.
Mm-hmm.
So now we can test what if the plane turns left while we look at it, or what if it turns right, or what if our camera rolls to the left, or what if it's shaking, and so on. So it becomes much, much harder to demonstrate that we have covered our domain with enough samples. And as a consequence, to have a reasonably safe system, we need to collect much more data. And collecting data is hard enough as it is.
Yeah, with no domains. Thank you.
Any other questions? Yes, Dumitru.
My question is the following. Do you use any compression algorithms to reduce the number of input to the neural network? Because the less input we have, like the more the performance we can get.
No, because basically any compression algorithm like that will lose data. And so let me show you again the video of what kind of things we can actually detect in the image. So this is pretty clearly seen there, right? So here.
Yeah, but
so this thing, it's few pixels across, and with my eyes, I could not recognize in this block of pixel a plane. But the system can. So
yeah.
So if we start using compression, then we lose the signal, and we can pick up a very, very faint signal currently. There are some compression systems that actually kind of do good job on compression. There is Dot Photon company, for example, in Zug, that does some very good compression that is aware of kind of sensors. They do compression with loss of data, but without loss of information. They only lose quantum noise kind of information from the images. So there are some compression techniques that can help. We don't use them yet. We may use them in the future. Currently, we don't.
Yeah, that was my point, because here we have some overexposed, like the clouds. for example, and it's just white, so we can just ignore this chunk of pixels there because it's all complete white, so we could really compress it without losing any data.
Actually, it's a bit misleading because what you see on a screen is an image that is limited to what the screen can show and what our eyes can see, right? So the actual data that is captured by the sensor may still have enough information there for the neural network to pick up a signal. Yes, Alexei.
If nobody asks, I will. So I probably missed the very first part of the talk. What is the ultimate goal of all this? To beat an autopilot, right?
So the ultimate goal right now for us, not the ultimate, but the immediate goal, let's say it this way, is to have aviation equipment with neural networks in it certified to aviation standards. So we want to have that DAL-A system that authorities agree to our story that it will fail less than whatever 1 in a million or billion times, that contains a neural network inside. And that nobody has done that yet. So currently there is no certified aviation system that has neural networks inside. And we're going to be the first. And the ultimate goal after that is to start building systems that use neural networks.
So just some future vision. So some point of time you'll need to basically kind of take the decisions based on ensemble of the output of the ensemble of that neural networks. And then basically your ensemble of neural networks represents kind of probability measure. And then you'll need to take the decisions on this probability measure or set of probability measures. And then actually it's quite interesting task because you probably interesting to see not only these probability measures, but how are you certain about them, how you're confident about these probability measures and how this confidence changes over time. So I think it's very interesting for me to see how it will move in future when it will be like a component in a more complicated system where it will rely on it.
So what I try to demonstrate here is that neural network component is actually not that different from any other component.
Mm-hmm.
So when you have a wheel on your landing gear, right? We test it very similarly to how we test a neural network. We would never have a complete confidence that this wheel will never fail, right? That's not the point. But we test it to understand when it can fail, under what conditions, and that even if it fails for whatever reason, we will not have loss of life. So it's the same approach with neural network components.
Yeah,
And the algorithms, the control algorithms, they are known for a long time. We don't even need neural networks in them, right? You have autopilots flying for decades. It's just that some parts there can benefit from having a neural network inside.
Yeah, but what I mean is like about how this confidence because pilot has the signals from different. He sees from his eyes, he sees by your system what happens around, and if he is not confident, because he's a human, he probably will not make some maneuver because he'll double checked 7 times, and this aspect is quite interesting how to solve. System.
So there is a good story about elevators, So if you think about elevator, it's very it's super scary piece of equipment. So think about it. You enter a room that doesn't have any exits or windows. It's a small claustrophobic room that is suspended on a rope over an abyss. And there is an automatic system without any human that closes the doors, locks you in there, and then moves you somewhere. And still we use these elevators without thinking all day. And that was not a smooth road. First elevators, when they just appeared, people were afraid of using them. So one crucial moment was in Paris in this fair that happens there, where one inventor has demonstrated an elevator safety mechanism. So you have a bar and over the elevator, a metal bar. And normally the elevator is suspended with a rope that is attached to this bar, and so the bar is bent. If the rope is cut, the bar straightens up and jams the elevator between the walls, so it doesn't fall.
Right.
So this kind of safety mechanism he demonstrated by being in this elevator where his colleague was actually cutting the rope, and he demonstrated that, even the rope is cut, I do not die. Still, for a very long time after that, there was this man in the elevator whose job was just to push the button. Remember, in films we have seen them. So it took literally decades until people trusted the elevators enough to walk there by their own. But it happened.
Yeah.
Okay. If we have no more questions, I guess we can kind of conclude.
I have the last one, probably.
Yeah.
What do you use? You told that you use actually the real data. So I know now this kind of trend of using synthetic, whatever, cartoons, let's call it, for neural networks to show this neural network to train. Do you have any experience with this and feeling?
Yes, of course. We also use synthetic data. So when we train, we mix in synthetic data. We have 3D engine to generate it, and it helps. And also for training, for example, the network that does this aircraft detection, what we do is we take a real image that we took in flight, and then we paint in it an aircraft using synthetic data. So we do use it, but we use it in training. We cannot use it in testing, because when we test how the network works, testing on synthetic data does not give us enough confidence that the performance is representative of the real performance. So while we use synthetic data for training, we use only real data for testing.
I see. Thanks.
So thank you very much for your attention.